Yeah, so I'm Andy. Struggling with the microphone still. Is that good enough? Can people hear? Oh. Okay. So hi, I'm Andy. I'm a postdoc at UCSF with Noah Zaitlin. I'm going to talk about bias you create when you condition on PCs in expression PCs in gene expression studies. So yeah, the intro is just going to be a bit on gene expression, but mostly graphical models, because acyclic directed graphical models are sort of the right way to diagnose when you do and do not want to condition on confounders or covariates. Then I'm going to show that, like, yeah, in fact, conditioning on expression PCs is conditioning on the bad type of covariates, which creates a bias. And then I'm going to actually talk about whether or not that's like of practical significance and when it is by doing some simulations. So yeah, like I assume everyone here knows gene expression data is like confounded by lots of things, right? And that includes both things you know and you may have measured, in which case you probably want to adjust for it, and things that you know and haven't measured and can adjust for, and things that you've never even thought of, presumably. And I think sort of similar problems come up in like DNA methylation and all these other functional measurements. And yeah, so I think it's pretty well known that principal components estimate confounders reasonably well under certain assumptions. There's like a huge amount of theory that I'm not going to talk about at all on that. And there's, you know, a million variants of PCA, and I'm not going to try and talk about many of them, but I'm going to talk about the main ones that we think are used in genetics for expression studies. And this is, I guess, yeah, so this is the graph. Whatever. Oh, sorry. Yeah, I screwed you up. Maybe just scroll down a little bit. Thank you. Yeah, so this is the sort of graph I have in mind with these gene expression studies. So, you know, you have X, which is the covariate you're interested in. It might be a SNP, it might be a treatment, it might be case control status. And it is affecting causally Y1, which is just one gene expression. And it's not affecting Y2, which I'm writing with this red arrow. And so, you know, the expression study is going to be to determine which genes X is and is not affecting. And what I've written down here is that this U1, which is my principal component or eigenvector, it's sort of in some sense created from these expression, right? Because it's just the principal component of the expression matrix. It's not like a formally correct graphical model, which I'll talk about a bit later. But so the reason I'm talking about graphical models is they allow you to determine when you should and should not condition on a covariate. And so something I hear a lot from people is you should always condition on every covariate. Like, I've heard this so many times. It's probably true that you should usually condition on most covariates. And this is an example of that. So I think this is pretty obvious to most people, right? So coffee and smoking are correlated because people who like to drink coffee apparently like to smoke. Smoking gives you cancer. I've read on the internet, coffee does not give you cancer. But, you know, as you probably all know, if you just sort of regress cancer on coffee, you're going to see an association, right? And also, as probably all of you know, if you condition on smoking, that goes away because conditional on smoking, coffee has nothing to say about cancer. So this is what people are talking about usually when they say confounding and why you should condition on confounder estimates. But it's not always true, right? And so here's, I guess that's fine. So this is sort of the other key example, right? So you have two parents, they're independently mating. Say we're talking about their height or something. If I tell you one parent's tall, that doesn't tell you anything about the other parent, right? But now if I tell you about their kid's height, now I say the kid is average height, and I tell you one parent is tall, the other parent's probably short, right? And so this is the exact opposite of what's happening in the other panel. Here you get a false positive if and only if you condition. Here you get a false positive if and only if you don't condition, right? And sort of the key distinction is these sort of arrows are colliding into this child, right? So formally it's an unshielded collider. And so when you see that, you should not condition. When you see this, you should condition, right? And sort of I think the intuition is like there's information flowing here that you block when you condition on smoking. And for some reason, you unblock it here, right? So there's no way for mom to talk to dad without the child. But when you sort of tell me about the child, you unblock the association. So you can go a little bit further and sort of say, if these connection strengths are like that, and you don't condition, you get an expected size of alpha times gamma, right? Which is just sort of the path length from here to here, which kind of makes sense, right? And then a similar thing happens over here. But again, the important thing is if you see a collider, you don't condition on it. If you don't, you do condition on it. So before I go back to graph stuff, I'm just going to say what PCA is. So when I think of PCI, I think of the SVD, just sort of like the standard decomposition. So, you know, this is orthonormal, that's diagonal. And so I guess I'm talking about these left singular vectors as the eigenvectors. You can talk about these, but they don't show up much. And these are, I guess, the eigenvalues or the singular values. So this doesn't look like a graph to me, right? This is a matrix decomposition. But it's, like, of course, equivalent to this, right? And so I'm just moving around symbols, and you get exactly the same expression, right? Just written in a different way. And now this does look like a graphical model to me, right? Because you have uj being created as a linear combination of a bunch of y's. And so the way I think of that is as this little graph right here, right? So the x is still the same thing, right? That's the thing we're primarily testing. And now at the bottom we have a bunch of genes, and each of them is sort of contributing to this u with whatever the relevant weight is, which is up here, right? And so what you can see is collider, and that's bad, right? So thanks. So collider, bad. So that's going to cause a bias, right? So just based on sort of analogy. And you know, if in fact this were just a strictly correct graphical model from that last slide, we would be able to read off the biases. You just follow the path. So if you regress x on some gene other than 1, you're sort of just going to get the path length from x to that gene, right? That's not, so that would be done if this was a graph, but the problem is this is not really the right graphical model, because as you add in x, the eigenvectors are all going to change, right? So in a real graphical model, these things are kind of chosen by nature, these weights, like these v1 and v's. But what happens is as you add in x, you start tweaking all the eigenvectors, right? And so they move from what you want to be regressing on. Because you want to be conditioning on the eigenvectors of sort of y before x gets in there. But you can't do that, obviously, right? And so it is approximately correct, though. And the reason is, well, under assumptions, right? So if alpha is small, the effect of x doesn't really do anything to y, right? So sort of to first order in alpha, it does behave the way a graphical model should. And then there's also sort of a technical condition on the, you have to have the first eigengap has to be large, because otherwise sort of eigenvalues kind of get mix-maxed and mix up, and bad things can happen. But sort of, under these assumptions, which I think are probably quite reasonable, right? Because if you're thinking of a sort of cis EQTL for x, alpha's tiny, right? And in real matrices, the eigenvalue spectrum looks like this, right? So it's almost always true that D1 is massive. But proving that these things are true is sort of the main work. So I guess I'll say a little bit about that. So the model I guess I have in mind is this sort of rank 1 confounder model. So you sort of start with this baseline matrix Y0, which is just sort of whatever, right? I let nature give it to me. It might be Gaussian IID noise, it might not be. It might be something really nasty. And you add this rank 1 confounder, and then the question is, if you regress on the principal components, how much bias does that add? Because what you're doing is you're regressing on the principal components you have, which are principal components of y. And what you want to be regressing on are principal components of y0, because this is the sort of uncorrupted bit, right? So it's probably true that principal components of this are going to be getting confounding, like real confounders. But what happens is when you start doing principal components of this, you get a little bit of x in there, right? So your PCs look a little bit too much like x, and that just sort of propagates through the pipeline and screws things up.
So wait, that's x, alpha t, alpha is your effect sizes?
Yeah, so now alpha is a vector, yeah.
Okay, so you're assuming that that's a vector that could be, x could be affecting every gene.
It could be, yeah. It could be. And so in fact, this equation has nothing to do with false positive or true positive. But it is, of course, true that if alpha has a 0 entry and if the pth entry of alpha is 0, that is a false association, and because the bias is non-zero, you will get a false positive, right? Sorry, I think I'm doing all of this stuff. Yeah, so, yeah, so, no, you're totally fine. Oh, there you go. Yeah, that looks real good. All right. Yeah. I feel like we're fighting. I lost my. I think I can't go.
I'll ask you another question at this point.
Yeah. Yeah. So, in the yeah, can we go? Yeah.
So why are you like?
Way back. Yeah.
I think there's an assumption about y that I don't understand. Is that you're saying that y actually has some real confounding factors.
So it doesn't. Oh.
And you're assuming that the principal components catch them, and so if you regress on them, then you're doing the right thing. But independent if you're doing the right thing, like I still don't understand. Like if you're quote unquote doing the right thing, why you still don't induce spurious associations between the y's and other.
Yeah, so if you're doing the right thing, that is correct, yeah. But if you're doing, but the right thing is impossible to do.
No, but I don't even understand why if you're doing the right thing, you still don't have any problems.
Oh.
Like what difference does it make if you're regressing on y0 plus alpha or x alpha t, or you're just you're computing for the components of y0? Don't you have the same problem?
So no. So the problem here is that
Would it still be a collider?
No. Well, okay. So
Like that doesn't like.
yeah, you're right. Well, it still sort of will be a collider, yeah. But that sort of gets to the heart of the fact that this graph is not actually exactly correct, right? So under certain assumptions, it works in certain ways. But what I mean by this is approximately correct is this equation holds to first order in alpha when the eigengap is large. The sort of things you're talking about are sort of taking my dumb example too seriously, I guess, is probably the problem, right? So you're correct, yeah, obviously. But I guess the thing that happens is when there's no x in here, right, you're just, there's no path from x to y1, and so there's no collider on the path from x to y2, right? So there is a collider, but it has nothing to do with the regression problem you're doing, and so it's not a problem, right? So if x had no link here, there would be no collider on the path from x to any of the other genes. Does that make sense?
Yeah, I mean, I kind of think of it like there's a confounder. Like the graph should have like some confounders with edges to the y's.
You could put those in, yeah.
And then I think the idea is that when you compute the principal component, you're somehow capturing that information.
So that's absolutely the motivation for doing it.
Yeah.
But it's true. But it's also true that the error in your approximation of that confounder is biased towards x when you add in x. And that's the part that screws you up. So I clearly didn't say that. So yeah, the problem, so conditioning on a known confounder, great. If a PC perfectly approximates a known confounder, obviously you can condition on it. If it's like almost perfect with like a little noise that is sort of pointing orthogonal to everything, whatever, that's fine. The problem is that the noise is looking a little bit too much like x.
Oh, I see. So you're saying that, I see. Okay, so you're trying to say that the PC will be a combination of approximating the true confounder plus the genetic confounder.
Yeah,
Okay.
yeah, that's actually the perfect thing to say, right? Yeah, so it's got a little bit of exactly what you want to be doing, and then also this other problem. And so on balance, it's not clear. Yeah, so in the simulations, it won't be clear what the actual, what one wins and which one's better.
I think the wrong was failed in the
That's all right. Well, I think it'll be fine. Maybe just
but maybe one of you guys can like shift
scroll. Yeah, awesome. Yeah. So let's go here. Wait. Let's do this one. Can you go up a little tiny bit? Yeah, awesome. Yeah, who else? Yeah, that's a good point.
I guess, do you want me to ask another question?
Yeah.
So no, this is really interesting. So have you thought about not really related to what you're talking about, but kind of related to what you're working on. Have you thought about under what conditions does a principal component capture the environment?
Capture the environment?
Confounder.
Yeah, there's like a huge amount of theory on this that I don't really have much interesting to say about. So like, I don't know, like, yeah, like that's like hardcore random matrix theory, right? So I don't have anything clever to say about that. Sorry. Yeah. I mean, the obvious answers are
In genetic, like if you
right.
apply that theory in genetics, like, you assume that we have some kind of like polygenic trait, and then you have like some confounder that would have some, like batch effect of every gene, like right then, what would, like, yeah.
So I guess not really. I think it's probably the answer. I don't have anything clever to say about that. Sorry. Have you? Do you have anything?
Well, for a long time we were writing papers on how you should use mixed models instead of PCs. So we were just saying that everything about principal components is bad. But I don't know. I mean, I think that actually the hardest issue that we found was that it's really hard to differentiate between the true genetic signal and the confounders. So especially if there's like a trans effect that affects like a lot of genes, then it comes up as a principal component.
Yeah. Yeah. So no. Well, I mean, I've thought about it, but I don't have anything to say. Yeah. I think it's hard. I think it's unidentified. Is like just my intuition. Like I don't know. I would be very keen to write that down in an intelligent way. I haven't, but I think it's impossible to split apart the sort of interesting low-rank genetic signal that's strong from environmental confounders. I mean, I guess people do it with like priors, right? So if you have a prior that an environment looks like this and a confounder looks like this.
We had like published a paper a couple years ago where what we did was, are the slides ready or is it?
We're just talking. Yeah. What? Yeah. I can only go right and left, actually. But yeah. That looks pretty perfect. Yeah.
So what we did was when we computed the confounders, right? We were looking for confounders that would affect only a fraction. We separated between confounders that affected all the genes versus ones that affected a fraction of the genes. The idea is that if it's a true biological signal, it's like a trans effect. It might affect 20% of the genes, but it's not going to affect 90% of the genes. So that's how we separate.
Yeah. So that's a prior, right? Yeah, and I think if you're smart about priors, that'll do it. Yeah. I'm not smart about. Yeah, but yeah. Yeah. So this is the things that we kind of tested, I guess. So yeah. So there's this little theory that says that there's bias and you can prove it, and that's the part that was hard to do, but it's not that interesting. So these are the sort of things that we've compared to. So I guess, as I eventually said, the problem with conditioning on PCs is they look too much like your covariate of interest X, right? And I think this is, yeah, so if you have this huge, large trans signal that conceivably might exist, that's going to look like a PC, and a PC is going to pick that up, and everything's going to go crazy, right? And so a sort of obvious first pass is to just project X out of your PCs. And you can either do that directly project out of the PCs, or you can project out of the expression and then do the PCA. It doesn't matter much. But the interesting thing is that this is a terrible idea. And so, yeah, so this is something Joel helped me a lot with. But sort of the nicest way to show this is if you just look at the t statistic for regressing your gene on your covariate, like this is what a t statistic is, right? It's the beta hat over the sigma hat. And if you condition on this residualized PC, because it's orthogonal to X by construction, it doesn't affect beta hat at all, right? But because you're adding another covariate into the regression, this can only shrink. And because this can only shrink, T can only go up, right? And so this thing that sort of seems like a clever way to avoid overcorrect correlation with X is actually just a T statistic inflation machine, right? And so I thought that was surprising. So this is a very bad idea. And I think others know that, right? So all of these papers are based on the fact that this is a bad idea. So SVA is one thing, and they sort of do, I guess, something quite similar to what you were just describing, right? So they sort of look for factors that are associated with sets of genes, and it's kind of like a sparsity type of thing by a Q value. And the interesting thing that SVA does is it allows you to tell it that X exists, right? And so because it knows X, it can sort of play this game of putting the right amount of signal into X and putting the right amount of signal into the latent factors, right? Because basically what's happening in this projected PCA is that your latent factors are perfectly orthogonal to X, and that's too independent. What's happening in ordinary PCA is they look too correlated with X, right? And so SVA is trying to sort of get it right down the middle. And so I guess NPure is another thing that sort of does similar stuff and also kind of can be told about this X guy. ICE, as you were just saying, is about as the mixed model version of these things, and it's also can be supervised either by REML or ML. And so the simulation setup is this thing I was talking about before, right? So you take some baseline matrix and you add a rank 1 confounder, and then you ask, so now this is super sparse, this rank 1 confounder. It just has one non-zero entry and on gene Q, right? And so what we do is you go along every gene other than Q, and we ask, is X correlated with the expression of these other genes? Because we know it's null, because we simulated the data, right? And so if these methods are working, you're just going to get perfectly calibrated null p-values, right? If they're not working, something will go wrong. And what will go wrong is that the p-values will be too low. So what we do is we use a KS test, just the simplest way of looking at a function, and ask if it's statistically different from just lying on the line as it should be. And then we do this a ton of times for a ton of different simulated data sets. And then we test those p-values to see if those are null. And so these are the sort of graphs you get out of it. So this over here is no correction, right? And as I've been saying, in this case, because there's no confounding, because that's how I simulated the data, this is perfectly confounded. This is perfect, right? If there were confounding, this would also be screwed up. And then there would just be no option, really. So that's what you're sort of expecting to see. And these are the p-values for testing whether or not these things live on the line. And they're all away from 0. And so the colors are just as I'm increasing the effect size of this uqtl. And in particular, once you get to blue, it's absolutely unrealistic. But that's not really the point of this part. And so what you see is, no correction perfect. These, I was surprised to see how well calibrated they are. So these are all conservative, right? Which, I prefer conservative to anti-conservative. So now these are the sort of more things that I think people, these papers, probably everyone in this room has used them. They have a huge number of citations, these things. And so this is the stuff that we have the theory for, right? So on the top row is, I'm just using k = 1 confounder. On the bottom, I'm using 20. The columns are different ways of estimating these latent confounders. And so this is the bit with the theory, right? Because it's just a regular PCA and it's just one PC. And lo and behold, if you make the signal really strong, you can see it, right? And presumably, if we spent lifetimes looking at those lines, you'd see something significantly different from 0 there also, right? As you go to k = 20, something weird happens that I don't know. If anyone can explain this to me, I'd be interested. But it's...
Can you explain, if you're above the line, you're conservative. If you're below the line, you're
conservative. Yeah, because it's a one-sided KS test.
What do you mean by supervised or unsupervised? Supervised means that you're taking into account X.
Yeah. Yeah, precisely, yeah. Yeah, precisely, yeah. So this is just the ordinary PCA here. And then you chuck in 20 components and there's clearly 2 countervailing forces, right? So this is doing this thing still, but something is making it anti-conservative, and I don't really know or care, I guess, that much. Pure, similar things, but pure is super conservative, actually. No, I shouldn't have said similar, and I don't know why that happens at all. So supervised PCA, so this is this thing where you project it out, and I said was definitely a bad idea.
How many PCs did you do in your unsupervised PC?
1. This one? 1, 20.
Pure, did you just run pure normally?
1 and 20. Yeah, normal, but I said, so here I said 1 factor, here I said 20 factors. But I think I tried to follow their how to.
You're pulling out 20 factors. So if you pulled out 20 factors of your PC, it would also, that's why it's super conservative.
So this is, so that's why this is happening, you think?
Or the second one on the top. Unsupervised pure. It's pulling out all the signal from the data. No, that's only 1.
Yeah. Sorry, yeah, so yeah.
You only pulled out 1 pure factor from the whole data?
Yeah. I think I've talked to a lot of people who've seen sort of similar confusing results here. So I don't have an answer. And then these guys are the thing I said was a bad idea, and look, it is a bad idea. And the interesting thing, is here I said if you don't supervise the PCs, if you don't get rid of this X, they look too much like X. So you get something that's anti-conservative. If you do tell it, you get something that depends on the effect size, right? So as the effect size gets larger and larger and larger, these eigenvectors look more and more and more like X, so the problem gets worse. Here you have an entirely different type of problem, because the eigenvector is by construction never correlated with X. But what does happen is, and so because of that, there's no dependence on the effect size, right? So in particular, you can have zero effect of anything. And if you, so you can have X that doesn't do anything at all. You residualize your PCs against it, and then you study, and then you ask whether it correlates with things, and you get super significant results, right? So that was surprising to me. And then again, in these sort of other supervised methods, which also know about X, same story, but they perform better, right? And that's presumably because they're, fancy versions of PCA. But it's the same thing. There is not a method that controls for confounding in this case, right, that I was able to find anyways. So those are sort of the existence proof simulations, I guess. This is more like, okay, in reality, it doesn't matter, right? So now I'm using, I'm still doing the sort of add a rank 1 confounder thing, but now I'm using real expression data. It's still simulated SNP. And now this alpha thing is much larger. It affects like 20% of genes and explains something like 5% of transcriptome-wide variation, which is crazy high for something like a trans EQTL, but super plausible for, I don't know, sex or case control status or whatever. And so what's happening over here is I literally have zero effect just for sort of seeing the global null, right? So X does nothing on these columns. And these are these sort of unsupervised methods that don't know about X, and these ones do know about X. And over here, I just have how many confounders I'm conditioning on. From none to 40. And then these mixed models I put over here. And so what you see is that there's no effect. Everything behaves totally fine if you don't supervise it with respect to X, right? Because of course it would. Oh, sorry, I should have said these are the false positive rates over, this is for each dot is one simulation, and I did many simulations, so there's many dots, right? And so there's a nominal false positive rate of 0.01, and these things are all kind of doing reasonably, right? Once you start but again, like I said, the supervised PCA thing just explodes, right? So there's no X signal anywhere in here, and you're still getting very significant results. More interestingly, when X is actually doing stuff, you get these sorts of plots, right? So the colors are the different methods. And what you see is sort of as you add more confounders, they all find more stuff and then find less stuff, right? And I think probably most people who do EQTL studies have plots like this. They probably only do one thing. But it's sort of, they're plotting the number of total positives usually. And the presumption is that most of those positives are true positives. So then they maximize the number of total positives, right? But if it's the case that there's way more false negative associations than positive, because that is the case usually, you're basically just mining false positive associations, right? And you're just sort of saying how many false positives can I get, and trying to put as many as possible into your bag. And I do think it's quite common for people to run these things this way, right? Without telling them about, like case control status or different tissues or whatever. And then again, but fortunately there's kind of a save, which is, if you do condition on X for these things, again, PCA does the stupid thing that we know it does, but PEER does much better, and SVA is, like, from a practical perspective, perfect, right? And I guess I should have said also, these mixed models are doing fine too, right? So there are solutions to this problem, and they're published, but people don't do them, I think. And so I guess the last thing to say is power stuff. So these were all false positives everywhere in here. So now these are the sort of true positives. And the main thing I see is that all methods perform very similarly here. And the things that have like greater p-values tend to be totally miscalibrated anyways. And so, I think if in practice you use SVA and tell it about X, you're fine. But, we were still kind of interested to see that you can prove there's a small problem for PCA. Yeah, so that's everything I have to say. Thanks. Part.
Is there a way to test this without simulation? So for instance, I don't know, you take the SNPs and the gene expression and then just
Yeah, so that would basically just be a different way of simulating a SNP, right? I guess it would be a more realistic SNP.
Oh, I see. Because in this simulation, you simulate the SNP, you don't simulate the
Yeah,
expression.
yeah, exactly, yeah.
Did you compute like the number of cis-ETLs in all different methods? So that's
Pardon?
like one of the standard things that how people compare power. They use cis-ETLs as a proxy.
Right.
I think it's got some biases in it actually.
Interesting. Yeah, so in this specific case, like SNPs are simulated and there is no notion of cis or trans. But yeah,
No,
you're
no, I'm
probably.
saying from real SNPs compared to real SNPs. The idea that we know that there are real cis-ETLs, and we know that almost every gene has a cis-ETL. So if you run the method and then you see more cis-ETLs, then that suggests that your method has found power.
I see, and you sort of, yeah, you compare the rates at which cis EQTL
Yeah.
hits go up to trans EQTL
it's not
hits.
perfect, but it's one of the ways that
Yeah. No, that seems really reasonable. Yeah.
Actually, I'll take back I'm not sure it's the same as simulation. Because if you have the same confounder, let's say relation structure, it's going to affect both the SNPs and the expression. So
But you're permuting the SNPs, right?
you're permitting the individuals. So you keep the LD, you keep all, you basically just permit the labels of the individuals in one of the data sets.
But you're only doing one SNP at a time, right? And they're expression PCs. So in our code, I can plug in anything for my X. So I don't know, but I'm sure you're right. I don't understand.
You were thinking about like one SNP at a time.
I'm not trying to do anything super clever. Yeah, I'm one SNP at a time for sure. Yeah, yeah, yeah. I guess maybe for the mixed model stuff, right? Especially, it might be important to be a little more. Yeah, maybe there it would make more of a difference, right?
Okay, so then if you have
No.
okay, so then I'm going back kind of once. So if you just do one SNP at a time, that's basically just like kind of case control
Yeah.
compared to the gene expression.
Yeah.
So then you can just randomly set case control based on the confounders. Because what you did is simulated basically the case control separately from the gene expression. But saying if the confounder affects the SNP.
Yeah, they don't have the correlation with the confounders that they should have.
Yeah, so you can simulate this. We can talk about it offline. We did it with the manipulation data, so
Yeah, that's clever. Yeah, I like that. Yeah.